okay, this is the problem we look for. It's the problem that's the easiest. It's the problem we have to recognize it being that way, though. I am not going to do this the long way. We're only going to do it the short way. You could do an ice table. The one thing I will say, it's very easy in this problem since these are both at 0.5 molar. Well, halfway to titration is going to be when I add 50 milliliters, and we're going to need that for our NaOH. We're going to need that for our graph because, again, they're the exact same molarity. If they weren't the exact same molarity, I'd have to, figure out how many moles I needed, and then from there turn that backwards into a volume. But I know that since they're the exact same molarity, I'm going to need 100 of the NaOH to completely titrate it, so midpoint is going to be 50. So that's going to be our X value on our curve. At the midpoint or the halfway point or anything, going back to this relationship we were trying to figure out here and looking at it the easy way, since half of the number of moles of NaOH you need are going to react, that means you're going to only have half of your original concentration or half of your original number of moles of your acid, and you're going to make that same value of your base. So your conjugate acid and your conjugate base are going to be equal to each other at this point. So in the Henderson-Hasselbalch equation, if they're equal to each other, the log of 1 is going to be 0, so pH is just going to equal pKa for this problem. And we've done this. We've taken the pKa a bunch of times now. Negative log of 4.5 times 10 to the minus 4, and that is going to give us a pH of 3.35. Oops, that's not 3.35. My brain was working faster than my hand. So now we have a point to put at 50 milliliters and a pH of 3.35. Again, we're going to look at the graph together at the end, and we'll try and make that graph so you can see what yours should look like, but I would encourage you to plot your points as you go.